My name is Amrita Kulkarni, and the topic for my project is parallel MRI with nonlinear inverse reconstruction. The goals of this project are to study the detailed concept of parallel MRI and to learn the existing techniques used for the same, mainly SENS and GRAPPA. To explore a new technique based on nonlinear inversion for image reconstruction in parallel MRI, and also the implementation of all of these techniques in MATLAB so as to compare and evaluate their performance. This project is based on the prior work done by Martin Ucker, and the main aim is to establish results which can be used to verify the methods that have been published in one of his papers, which can be retrieved from the given website. The advantage of using parallel MRI is that it reduces the scan time because we undersample the case space using lesser number of phase encodes. The two widely used techniques in parallel MRI are SENS and GRAPPA, but they have some drawbacks due to which we obtain degraded images for high undersampling factors. Hence, we need to use an alternative method for reconstruction which is more sensitive to image artifacts. So a new method of nonlinear inversion with regularization can be used for better reconstruction. In this figure, the square at the center is the object that is being imaged using 4 coils that are shown in red. Each coil will detect signals which fill the case space, but this case space is undersampled for faster speed. Due to this reason, as we can see in the 4 reconstructed images, aliasing artifacts are present. But these artifacts can be removed by using the knowledge of coil sensitivities. Now one can easily conclude that the circle is the brightest in the top right image, which implies that it must lie somewhere in the top right part in the actual object, whereas the plus sign is the brightest at the top left image, which means that in the object being imaged, it lies in the top left part. And similarly, conclusions can be drawn for the other parts of the image. Hence, every coil is sensitive to a particular area of the object near which it is placed. This information can be used in order to reduce the artifacts and unfold the image. This results in the image shown to the right, and we can see that now it is free of artifacts. This concept of parallel imaging is further extended in two types of techniques, which are SENS and GRAPPA. Let us look at SENS first. Now we can see the 4 aliased images obtained from the 4 undersampled case spaces respectively, where each case space belongs to a different coil. What SENS does is that it first generates the coil sensitivity maps and then performs reconstruction of the image. It uses matrix inversion process to unfold and combine the aliased images from each coil to get the final image. SENS operates in the image domain where it reconstructs and then corrects the images. Unlike SENS, GRAPPA operates in case space domain where it first corrects and then does reconstruction. As we can see in the figure, case space is acquired but it is undersampled. The missing lines of case space are filled with the prior knowledge of coil sensitivities, and this is followed by a Fourier transform to create alias-free individual images from each coil. These images are now combined using a sum of squares method to get the final image. The third technique that can be used is regularized nonlinear inversion. In this technique, generation of coil sensitivities and reconstruction of the image is done simultaneously, whereas in SENS and GRAPPA, it is done in 2 different steps. The flow of how this technique operates is as shown. So at the beginning of the reconstruction process, the coil sensitivities and image content are initialized and treated as an estimate. The undersampled case space data obtained from individual coils is taken, and the undersampling pattern along with the weight matrix is obtained. Now, it calculates the difference between the available case space data and the Fourier transform of the estimated coil sensitivities. This difference is used as an error value which needs to be minimized. To do so, the sensitivity profiles as well as the image content is simultaneously updated with the help of conjugate gradient algorithm. All this is performed by using multiple iterations of steps from 3 to 7. After certain iterations, coil sensitivities converge, so they are not updated any further, and only the image content needs to be changed in the next iterations. After an adequate number of iterations are performed, a reconstructed image is obtained with minimum artifacts. This reconstructed image then undergoes post-processing, which then gives the final image. These are the coil sensitivity profiles that were obtained after 5 iterations for 8 coils. As we can see, every coil is sensitive to either of the 4 corners or of the 4 edges of the object being imaged, and this is dependent on the way they are placed. We can see why post-processing needs to be done to get the final image by comparing the image before and after post-processing. Let us now see the effect of increase in the number of iterations. The above images have been obtained for an undersampling rate of 2. The image obtained after 5 iterations is somewhat blurred and aliased. Increasing the number of iterations to 10 gives a better image, but it still has some aliasing at the center. After 20 iterations, we get a very good quality image with perfect edges and no aliasing. I implemented all 3 techniques discussed before in MATLAB by using images obtained from an 8-channel head array coil. This is the original MP-Rage image taken from a fully sampled K-space and is used for the analysis of different techniques of reconstruction from undersampled K-space. All the techniques use auto-calibration, where the central area of the K-space is fully sampled, whereas the rest of K-space is undersampled. Here, the acceleration factor is 2. We can see that the image from sense has many artifacts and it is blurred. Grappa and nonlinear inversion give better reconstructed images, but Grappa has some amount of noise in the central part of the image, which is evident at higher acceleration factors. These images have been reconstructed from K-space, which was undersampled at a rate of 3. Again, sense gives poor results. Image from Grappa contains quite a lot of noise, whereas the image from nonlinear inversion is closest to the original image. Here, the acceleration factor is 4, and we can see how the image from nonlinear inversion has degraded due to aliasing in the central area. Grappa also undergoes aliasing and contains noise. The main drawback of nonlinear inversion is the amount of time for reconstruction, because at higher undersampling rate, a large number of iterations are required, and this leads to longer time for reconstruction. As we saw in the results, the quality in central areas of the image begins to deteriorate as the acceleration factor increases, and hence nonlinear inversion fails to produce artifact-free images for very high acceleration factors. The lessons learned are that sense produces aliased and blurred images. Images obtained from Grappa are corrupted by noise, and they contain considerable aliasing for higher rate of undersampling, as we saw earlier. Images from nonlinear inversion have comparatively less artifacts. In nonlinear inversion, coil sensitivity profiles are obtained from all the available K-space data and not just the central part of K-space, whereas in sense and Grappa, only the central part of K-space is used. Aliasing can be eliminated by increasing the number of iterations. The conclusion is that regularized nonlinear inversion is an efficient technique of image reconstruction for parallel MRI, as it gives satisfactory results. The process of image reconstruction and estimation of coil sensitivities is simultaneous and iterative. This method has markedly improved the achievable image quality at high acceleration factors, and it performs better than the other conventional methods. These are the references that have been used. Thank you.